Welcome to Unit 7, Lesson 1. This lesson is going to focus on introducing reciprocal functions and reviewing transformations, which we've covered a lot this year. We've covered them in every family of functions that we've looked at, but we're going to look at transformations specifically with reciprocal functions, which will serve to help you see a new context in which to apply them and review them in preparation for some of our end-of-year exams. So first, I want to really get into the vocabulary here. Why is this called what it is? So intro to reciprocal functions. What is a reciprocal? So I'll pause for a second and I'll just let you think about that. What is a reciprocal? Well, you might be thinking of a reciprocal as flipping over a fraction. And so one of the most common ways that we think of reciprocals is something like this. You might be asked, what is the reciprocal of 2/3? And you would say 3/2. And so a reciprocal is when you flip a fraction over. Simple as that. Sometimes they are also called a multiplicative inverse, okay, which is a much more mathy word, but I think most of us are more comfortable with the word reciprocal. So you might think of what is a reciprocal? Well, a reciprocal is the flipped fraction, I guess. It is a flipped fraction, or I guess that's the best, we'll just leave it there. Now, to apply that, what is the reciprocal of 2? So I gave you an example of a fraction that clearly has a numerator and a denominator. And so you see like 2/3 and we flip that over and it becomes 3/2. 2 is a little bit dicier because we don't see the denominator on the 2, but really it is 2/1. And so the reciprocal would be 1/2. And we use that relationship a lot if we want to say we have a coefficient of 1/2 and we want to get rid of it. Instead of it dividing by 1/2, we would instead multiply by 2. We'd multiply by the reciprocal. Now, what is the reciprocal of x then? So the reciprocal of x, that would be x/1. Oh, I don't want to have an equal sign there because it's not equal, so we definitely don't want to do that. It would be 1/x. And so the reciprocal function is actually y equals 1/x. It is the reciprocal of the function y equals x. Okay, so that gives us a little bit of vocab background there. So what are reciprocal functions? I'm going to do this out like pretty basically. I don't have space on the screen here to put Desmos in. I actually paused the video like a hot second ago and inserted Desmos into a future slide. We'll see if it works. I don't know if it'll work. So the parent function is f of x. I just gave this to you on the previous slide. F of x is equal to 1/x, or if you would prefer, you can say y equals 1/x. You can use whichever notation there you like. And the sketch of this, so if I had Desmos out, we could go and sketch it, but the sketch looks something like this. So you've got your x-axis and your y-axis, and there's actually 2 branches to it. Okay, you've got a branch that looks kind of like a decaying exponential there. It's getting very, very close to the y-axis and it kind of curves down. Let me see if I can turn my pointer on because I'm pointing, but that is not helpful to you. So it starts up here, or I don't know if it's coming down from above. I don't know if you want to say that's where it starts, but it's coming down from the y-axis and it's really, 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 really close to the y-axis, and then it curves and now it's going to get really, really, really close to the x-axis. And there's another branch to it, which is over here in the 3rd quadrant. And that was super messy. Let me see if I can give you something a little bit better than that for your notes. Something like that maybe. Okay, and this one does something similar where it's coming in super, 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 super close to the x-axis, and then when it starts to curve down, it will get really, 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 really close to the y-axis. All right, so a couple of key questions here. What happens when x is equal to 0? So looking at our graph, when x is equal to 0, so here x is negative, and over here x is positive, and right here is where x is equal to 0. And we've got these 2 branches of the graph, and they're both getting close to the y-axis where x would be equal to 0, but they're not actually getting there. There is a break in the graph. So you can think of it as there is this branch over here, and in order for you to draw the whole graph, you have to take your pencil, pick your pencil up off the page, move it to the other branch, and then sketch the other branch because there is a break in the graph there. Now, another way that you could look at it is come back here and look at the function. We cannot divide by 0. So I do want to pause on that for a second, okay, because this is a major issue for a lot of people. You can have 0 divided by 1, okay? That is 100% fine. That is equal to 0. That is like saying I have 0 ice cream cones and I'm going to divide them by, like, I guess in this case, 1 person, but okay. So how many ice cream cones do I have? None. If I have 0 ice cream cones and I'm going to divide them evenly between 5 of my favorite students, how many does each one get? 0. It was like a fake offer. I didn't have any ice cream cones. So that is fine. It's like mean, but it's fine. It's not mathematically impossible. If you have 1 divided by 0, that is actually mathematically impossible. Suppose I have an ice cream cone and I divide it between 0 people. How many ice cream cones does each person get? That is a nonsense question. I just told you there were no people. If there are no people, then the question, how many ice cream cones does each person get, is a nonsense question. It's completely illogical. You can't ask the question, how many does each person get, when there are no people. That is an undefined operation. I don't have quite enough space there to write it, but undefined. It doesn't make any sense to divide by 0. It's taking something and saying, I am going to put it into nothing. How does that work? Like you have like a portal or like what? That just doesn't work. It is a nonsense situation. It doesn't make any sense. To have nothing and then spread your nothing out between everybody. Awesome. But you can't go the other way around. It's nonsense. So the idea of putting a 0, like doing 1 divided by 0, is completely illogical. It doesn't make any sense. So for that first question, what happens when x is equal to 0? There's a couple ways you could say it. You could say there is a break in the graph. Okay. It's actually called a discontinuity. Okay, which is the same as a break. Okay, or you could say like the function is undefined. Like, that is just not a thing that can happen. And when you have something that's undefined, the way it shows up is it shows up as a break in the graph. Like you can't have a graph there. Like there is no value. There's no value that you can get for this. It's not a thing. All right, next question. What happens as x approaches 0 from the left? So that is a very pre-calculus phrasing of that, where we talk about like approaching, and we approach from a direction. So we've established that when x is equal to 0, we don't have a graph. So now we're going to ask, like, what happens as it approaches from the left? So from the left is over here. This is my left side. And we're going to trace the graph. So we're going to make x closer and closer and closer to 0. And as x is getting closer and closer and closer to 0, my graph is going down to infinity, okay? And so it's basically like tanking. It's going further and further and further down. So you might say that as the that y, we could say y, and then the right hand arrow is read as approaches, so that's y approaches negative infinity. In other words, it goes down, and it usually goes down very, very steeply. Okay, so you could say it goes down. There is some notation from that you could see. It's like x approaches like 0 from like, and then you might have like a negative, like to indicate the direction you're approaching from. But try not to overthink it. So approaching means gets close to. So as x gets close to 0 from the left-hand side. So you're over here, which leads us to our next question, which is what happens as x approaches 0 from the right? So the right-hand side would be over here, and we're going to make x smaller and smaller and smaller and smaller. So we trace this, and we'll notice that as x approaches 0 from the right, our graph is actually going up to positive infinity. And so we might write y approaches positive infinity. And that just means it's getting bigger and bigger, like it's exploding. Okay. Last question there is, can y ever equal 0? So is there a number that you could plug in for x that would make your y value equal to 0? So you might want to just stop and think about this for a second. If you plug in a positive number for x, a positive divided by a positive is going to give you a positive, okay? And so if you plug in a positive number, so something over here, you're going to get a positive. If you take a negative number and plug it in, a positive divided by a negative will always give you a negative. So you got negative. Now you might say, well, what about x equals 0? There is nothing there. It is undefined. So the answer to that is no. And there's a couple ways you can reason it through. That is one way. That's an algebraic, using the equation and saying, like, listen, I put a positive number, I put a negative number, and there's nothing else to put in because you can't use the 0. Or you could look at the graph, okay, is another way you could reason that out. Is look at the graph. Y is equal to 0 would be on your x-axis, and what you've got here is it approaching from the bottom, and over here you're approaching from the top, and you're not ever actually getting to the x-axis, so you're not ever getting to where y is equal to 0. Either of those lines of reasoning is fine. I want you to go with the one that makes the most sense to you, but also it's good to be able to do it both ways, to be able to have something make sense from the function and then also from the graph. So quick review of asymptotes. This is the illustration Escape from Algebra 2. I did this in our lesson on exponential graphs, and I stood in the front of the room. For those of you that were here, I stood in front of the room, and I said I want to escape from Algebra 2, and I said, okay, before I can get to the door, I got to go halfway to the door. So I'm going to go halfway to the door and cover the distance. And look, I can draw a picture. Okay, so if you're familiar with my room, all right, here's you guys as my students. There you are. And then the door is right here. And here's me. Okay, and I want to escape. Okay, I've had enough. I'm quitting. And before I can get to the door, I've got to go halfway to the door. And you can see that I am closer to the door, but I am not at the door. And so I am going to go halfway to the door again, and you go like half the remaining distance. And I'm still not at the door. And so I'm going to go halfway to the door again. And each time I'm actually covering less and less distance because half of the remaining distance is less. But no matter how far I go, like I still have half the distance left to go. And so in practice, I'm eventually going to hit the door because I can only take steps that are so small, and my shoulders actually have width to them. And so I'm going to slam into the door. But theoretically, from a math standpoint, I'm never, ever escaping from Algebra 2. I can't get out. I can't get to the door because I will always have, if I'm always cutting the distance in half, I will always have more distance left to cover. And so in math, no matter how small your number is, you can always find a smaller number. You can always divide it by 2 or 3 or whatever you want to divide by. You can find a smaller number than the one you have now, and you won't be at 0. You can find something that's smaller. So that gets to the idea of the asymptote. The asymptote is a line that the graph gets close to, but will never, ever, ever touch. It's just going to keep getting closer and closer and closer and closer and closer, but it's never getting there. And when we're graphing reciprocal functions, we actually have two asymptotes. So a reciprocal function has two asymptotes. It has a horizontal asymptote, which we saw with our exponentials, and a vertical one. So it's got a horizontal asymptote and a vertical one. So it's actually got two. If you are asked for the equations of your asymptotes, horizontal lines have an equation of the form y equals some number, okay? And so I'll just do a quick little example, like y equals 2, okay? That would be a horizontal line, 2 up, okay? 2 up. I am getting so many text messages right now. I keep looking at my watch. My phone is over here and it keeps lighting up. Okay, and vertical lines have the form x equals, and so you might have something like x equals 1, and that's the equation of the vertical line, and you go like 1. I want to make sure I got to do this backwards. Actually, I have no idea how this is going to show on the video, but for me, this is 1 to the right, but on my screen, it looks like it's 1 to the left. I don't know. So there are two different asymptotes there, and hopefully you did not listen to this on mute, because that's not going to help you a whole lot without the explanation. All right, so we have our exploration of the transformations, and so the directions there say state the transformations, the equations of the asymptotes, and the domain and range for each function. I have, because at the time I'm recording this, I don't know if I have jury duty the day that you might be doing this, because I don't know, I'm not going to find out until later. But you've got a handout. This is maybe not for the year that you're doing this, depending on what year. You know what? That's not going to help. We're on the back, okay? So you should like flip it over, and you're on the back. And there's space for transformation, asymptotes, domain, and range. I don't have space to write all that on the screen, so you are going to need to listen, because I will tell you the answers. Okay, I'm going to demonstrate it on Desmos, but you're going to need to listen. So if you've got it on mute, now's a good time to take it off, if you know that I said that. I say that because people do videos on mute all the time. Okay, so let me go, and I have to deactivate the pen to activate the graphing calculator, and that just changed my whole window. All right, so to do this, let's go ahead and graph the parent function. It's always good to see the parent, and that's what I told you it was, so I wasn't lying to you. And you can really see those asymptotes there. If we come over here and like hover over it, we can like trace and see how the y value is getting smaller and smaller and smaller and smaller and smaller, and so small. That's kind of weird that it did that. There it goes. It's going to keep getting smaller and smaller and smaller, but it's never ever going to be 0, because a positive divided by positive is not ever going to give you 0. So let's look at the next one, which is y equals 1 over x minus 3 plus 4. And so this is, you can see why we don't do transformations starting with these functions. We start with absolute value because it's much, much easier to see. But the concepts are the same. So stating the transformations, what I want you to kind of home in on is this center point here. I don't know if you can see my mouse or not, but look at the origin, and then look at where that blue function has kind of shifted up to. And we can see that the blue function goes to the right. Okay, so this branch down here has gone to the right. I'm a little afraid to click on stuff because this is the window where if I click off, I can't come back. And it's gone to the right, and I can also see that it's gone up. And if you look at your equation, I can move the cursor around. The equation, you can see we have a minus 3, which means to the right 3. And remember, the left and right is the inside. So when we're dealing with a reciprocal function, we are dealing with the inside of the fraction, which will be the denominator. So we're inside that denominator. So a minus 3 inside means that the function goes to the right 3. And a plus 4 outside of the function means that it goes up 4. Now, it also asks us for the equations of the asymptotes. So I'm going to show you a couple things. Because I have gone, oh gosh, there's a couple ways to do this, but I have gone to the right three. The vertical asymptote will be at x equals 3. Now, you can do something if I click, not there, here, I clicked on the settings, I can actually change the line type. So the vertical asymptote is not part of the function. Typically we'd use a dashed line. And so what that does is it changes that to a dashed line so you can see it a little bit better. And so I can see that the vertical asymptote is at x is equal to 3. Okay, and I'll let you really look at that. Let me hide the red one. Just click on that. And so because the red one was maybe cluttering it a little bit. So you can see that there's a vertical asymptote at x is equal to 3. It also goes up 4. And so for my horizontal asymptote, I'm going to be looking at y is equal to 4. And again, I'm going to click on that settings and click on the purple. And I'm going to do a couple things. I'm going to change it to green so that it matches, and then change it to a dashed line. And so what I did was I changed my asymptotes. So my asymptotes were both the same color, and then I changed them to dashed lines because they're not really part of the graph. Okay, they are the equations of the asymptotes. Those are the lines that it's getting closer and closer, but not ever getting to. Okay, closer and closer. So for your answers, okay, we'll keep going over them. It goes right 3, up 4. Those are the transformations. The vertical asymptote is at x is equal to 3. The horizontal asymptote is at y is equal to 4. Now, another way you can get that is, remember, you can't divide by 0. So if you could say, well, x minus 3, I'm going to try to click on over to the pen and hope I don't jack this up. If you look at your denominator, oh, it's on, hang on. There you go. Okay, if you look at your denominator, you could say like x minus 3 equals 0. Like, what would that be? Add the 3 to both sides, and x is equal to 3. So you can find it that way as well. Now, the last question there is saying the domain and the range. So the domain is all of your possible x coordinates. So if I look at my x-axis, okay, I have a break right there at the asymptote. And so pretty much it's all real numbers except where you have the asymptote. There is a break in the graph. And so there's a lot of different ways that you could write that. Popular ways are this. Okay, so the two popular ways would be to say negative infinity up to the 3, and then from 3 up to infinity, and you use the parentheses to indicate that the 3 is not included. Okay, so if you had a bracket, the 3 would be included, but there's no, like, we're using the parentheses, which indicate negative infinity up to the 3, and then, but not the 3, and then not the 3, up to infinity, all real numbers. The other thing you could do is you could say, like, domain, you could say x minus 3 cannot be equal to 0, and then add the 3 to both sides, much like you would for the other calculation. And you would say the domain is x cannot be equal to 3. That's the same as saying, hey, all real numbers except for the 3, not the 3. You can do the same thing with the range, and I'll do that with the graph, though. Let me get all that out of there. So you could go on your y-axis, and it's literally going to be all real numbers except where you have that asymptote. And so you could say the range is negative infinity up to the 4, but not including the 4, unioned with 4 to infinity. And so that's like a way of saying, hey, it's negative infinity to positive infinity, but there's a break at the 4. You could also say y does not equal 4. Okay, would be another acceptable way. So because I'm not writing all those down, I will go over the answers again. So transformations right 3, up 4. Location of the asymptotes, x is equal to 3 and y is equal to 4. And the domain is x does not equal 3 and the range is y does not equal 4. Why? Because there's an asymptote there instead. Like there's no graph there, there's an asymptote there. All right, so hopefully you were able to catch all of that. Rewind the video if you need to make sure that you have all of that filled in on your sheet. Okay, and your notes are complete. All right, let's see if I can turn off this and we'll come back to this. So we'll put that back on and we'll delete those. I'm going to regret that I did that. All right, second one. And you can use f of x and you can use the y in Desmos. It does recognize both. And so, and I just realized I did not erase all my scribbles on the Go me. Let's erase all that. There we go. Okay, so for this one, let's take a look at those transformations. So on this one, the black graph there, hopefully you can see that it's gone down, like it has shifted down. And that -3 from the equation should be a little bit of a tip off. It also has flipped over. So the piece of this that was up here, okay, it flipped over and then it went down. Okay, so yeah, I flipped it over and then went down, and then this part here like flipped over and went down. It also, if you look at it closely, this is really, really hard to see, that it got stretched out a little bit. It doesn't quite match up. So you got that 2 there that is doing a vertical stretch. Vertical stretch is really, really hard to see. So if you're thinking, I'm just going to take your word for it because I don't see it, that's fine. When we first introduced vertical stretches, we do it with things like absolute value and parabolas that are easier for you to see. Like, yeah, that got like stretched out vertically. But on this one, like I don't really see it super well either. I can see it, but not really well. All right, so that pretty much covers the transformations. So as before, I'm going to turn that one off so it's not cluttering it out. So we do have a flip. So on your worksheet, if you're following along, transformations, it is flipped. You could say it's flipped over the x-axis. Actually, flipping over the x-axis and flipping over the y-axis, you can do both. They're going to look exactly the same. So if you just want to say flip, that is fine. It also has a vertical stretch because of the 2. So whenever we're multiplying, so we had a 1 and like 1 times 2 is 2. So when you're multiplying, it does vertically stretch it. Again, if you don't see the vertical stretch, that's fine. It is hard to see. And then that -3 means it went down 2. So if you need to pause the video and make sure you have time to write that down, it has a flip, a vertical stretch, and it went down 3. Second part is looking for the equations of those asymptotes. So let's look at the vertical asymptote. Yeah. Okay, we'll look at the vertical asymptote first, and that's going to take the form x equals. Okay, so it's going to take the form x equals, and that would be where is there a break in the graph. So I'm like traveling along my x-axis, and I can see that when x is getting equal to 0, that's where we are seeing the asymptote. When I put in x equals 0, you can see it better. Okay, and then as before, I'm going to go into the settings, and I'm just going to change the type of line that I have there because it is a dashed line and it is the same as the y-axis. So x equals 0 is the equation of the y-axis. So that is my vertical asymptote at x equals 0. My horizontal asymptote, okay, I know that it has gone down 3 units, and so I'm going to try y equals -3. And when I get that in there, it does look like it corresponds. And you guys are allowed to use Desmos to do this. So if you're not sure, you can like type something in. So let's say you typed in like y equals 3. As soon as you put it there, hopefully you're like, that is not the asymptote. And that prompts you to go back and check something else. out. And I'm going to go click on that, and I'm going to change the color and the type of line just so my asymptotes do match what I had before. And so my asymptotes on this one would be x equals 0 and y is equal to -3. If you are noticing a connection between the transformations and where the asymptotes are, yay, there is. They're like very related and also related to your domain and range. So let's go tackle that domain and range. We'll do it a little bit faster this time. So as I am traveling, I don't think I want red though. Let's do blue. So I'm traveling along my x-axis, and then I have a break right there. That break happens to be when x is equal to 0. So two different ways you can write it. You can say it's -infinity to 0, but not including the 0, unioned with 0 to infinity. Or you could simply say, hey, x does not equal 0, okay? So x is everything, but not 0. There is a break in the graph at 0. When you're doing your range, you go traveling on your y-axis, and there's a break right at the asymptote. And that break is at y is equal to -3. And so for your range, you might say -infinity to -3, unioned with 3 to infinity. Or you could simply say y does not equal -3. So again, to recap, since you're trying to fill in all kinds of stuff on your worksheet, I hope. Transformations, flip, vertical stretch, down 3. Vertical asymptote is at x is equal to 0. Horizontal asymptote is at y is equal to -3. And then your domain is everything but 0, pick however you want to write it. And your range is everything but -3, pick however you want to write it. So that actually completes the entire lesson portion. On your own, there you have an assignment, at least the year that I'm recording this, okay? Like always like a disclaimer there. So to be turned in on a separate piece of paper, you have 2 problems just like this one. State the transformations, the asymptotes, the domain, and the range, okay? The other 3 are just asking you to explore different kinds of rational functions. And so the other ones are going to ask you to graph some stuff. So for example, let me hide these. What happens if you square that? Oh, you know what would be better is if I made that. Yeah. So it's going to do some stuff. And so you've got some, and what you're supposed to do with those are sketch the graph, state the asymptotes, go ahead and like graph what you think they are, but like and check them, like play around with that on Desmos, and give me the domain and the range. So the domain and range should be everything except where you have the asymptotes. So make sure that your answers for the asymptotes and your domain and range at least match with each other. So if you got one of them wrong, the other one should go wrong with it. Question 5 is going to do something kind of weird. And then question 6 is going to ask you to explore with that. So those are the 2 that are on your own. If you need to pause this, if you're trying to do this from home, you don't have the worksheet, go ahead and pause here and copy those down, like transformations, equations of asymptotes, domain and range. Those are just like the one that I just did. And then these sketch the graphs, write the equations of the asymptotes, and state the domain and range. And you can pause the video here or rewind, do what you need to do to get that done. And then for number 5, what do you think is happening when x is equal to 3? Okay, because you're going to look at the graph. Okay, and then you've got that denominator with the x minus 3, and we know the denominator can't be 0. So what do you think is going on there? So go ahead and complete that. That is to be turned on a separate piece of paper.